Hello everyone, I'm Nima Samkhaniani, and in this presentation I would like to talk about the numerical simulation of drop impingement on a heated hydrophobic surface. The motivation for this study was in a diesel exhaust gas after treatment system where the AdBlue injected to the exhaust gas to convert the NOx into the ammonia and water. We know when the AdBlue injected a liquid film form on the wall, the evaporation of this film create some solid deposit which impair the performance of this system. So our goal is to avoid film formation, and to understand how to do that, we need to understand the outcome of drop impact on a heated solid surface. From the literature, we know when a drop impact on a solid, we have three regimes, including deposition, rebounding, and splash. Our favorable regimes are splash and rebounding. So the criteria and the parameter which accelerate this transition would be beneficial for us. We know the parameter affecting on the drop regimes. It's include the drop impact velocity, initial diameter, which can be seen in the dimensionless parameter like Weber number and Reynolds number. And also, the other important parameter is the morphology of the wall. The wall can be hydrophobic, or super hydrophobic. To convert a smooth hydrophobic to the super hydrophobic surface, we need some micro post structure on the surfaces to convert them to become a super hydrophobic surfaces. We know this parameter effect on the drop behavior during the drop impingement. We are going to study it numerically. For numerical investigation of this problem, we have a different method, sharp and interface method. In the sharp interface method, the interface locate in one cell, but in the interface, but in the diffuse method, we have a region where the interface locate in a region, not in a single cell. We can use all these methods given here for a simulation of such a phenomena. Here we use the open foam. In the open foam, we can use the interfoam and inter-isofoam, which uses the VOF method. However, we decide to implement our phase field method in the open foam. Our reason for to develop this method in open foam was that interfoam, or generally VOF and sharp interface method, suffer from the space current at the interface, and this space current can be large when the surface tension is important. Here we deal with some small droplet where the surface tension is important, so this parasitic current can distort the shape of the droplet and behavior of the droplet in contact with the wall. So we use the phase field method. As you can see, phase field method in parasitic current in phase field method is much smaller than interfoam. Also, another advantage of using a phase field method compared to VOF method is that we can handle the interface motion along the no slip boundary condition automatically. If we want to talk about the phase field method, here we solve the Cahn-Hilliard equation. It's similar to volume fractions we use in the VOF method. However, here in the right-hand side of equation, we have the mobility and chemical potentials. Cahn-Hilliard equation solve the order parameters. A transport equation for the order parameter. The order parameter changes from the -1 to 1. In a diffuse interface, the thickness of the diffuse interface somehow is related to the capillary width and the mixing energy. Also, we beside the Cahn-Hilliard equation, we solve for the continuity equation as Navier-Stokes equation, and also as heat transfer is important here for us, we solve for the energy equation. For this study, we consider all the thermophysical properties constant except for the surface tension. The surface tension is dependent to temperature. This dependency of the surface tension to the temperature create some extra terms in the chemical potential and surface tension. To calculate the thermophysical properties in the interface region, we need to interpolate the data. For the interpolation, we use the density and thermal diffusivity with the arithmetic interpolations, and for the viscosity, we consider the blended scheme. Also, to close the equation, we need to consider some data for the capillary width and mobility and mixing energy. Capillary width calculated from the Kahn number and our reference lengths. Here in this study, reference lengths would be the initial diameter of the droplet, and the Kahn number is always considered 0.01, and the mobility is somehow considered as a square of the capillary width. And there is an unknown prefactor, which is in the phase field method calculated based on the comparison with experiment. In our study, we always use this prefactor 1, and it shows that this prefactor, with this prefactor, we get a good result. If you want to give you a general information about the phase field method, this code have been developed with Dr. Holger Mosher from the Darmstadt University and Dr. Martin Warner in KIT. The solver is implemented in open form extended 4. For detail about the implementations and the validation of this solver, you can refer to the mentions papers. Here we again validate this solver for the heat transfer as we implemented in this study. For the validations, we consider a drop motion in a stagnant liquid. The droplet motion is due to the temperature gradient and due to the Marconi effect. Our comparison with the analytical solutions and previous sharp interface method numerical simulations shows that the performance of our solver is better than previous numerical simulations, and we can touch the analytical solution. So it shows that our solver can handle heat transfer accurately. For the main problem, we should consider the drop impact on the solid. For that, we consider an axisymmetric domain. For the wall, we consider no slip for the velocity and a fixed temperature for the wall. Here, the temperature of the wall is smaller than the saturation temperature, so we don't have any evaporation or phase change in this study. We made a lot of numerical simulations. For the validation, we consider the water drop impact, and we made a simulation on a various contact angle and Weber number, and we somehow get a good result for a different range of study. And also we could get the whole detail of the physics from the, as you can see, we have a different regime, no air bubble, floating air bubble, and stick air bubble, and all of them can be captured with the numerical, our numerical simulations. Here you can see a drop impact. As you can see, all details are captured accurately. We can get the capillary wave, also the air entrapment, air floating, and everything could be captured with the solver. After we understand that the solver can get this physics accurately, we made not just visual comparison. We made some quantitative comparison. The two most important parameters was contact time and spreading ratio. Our comparison with experimental shows also again good agreement. After we get confident about the solver, we made other simulations. Here we use the oil water solution droplet to understand the criteria between the rebounding regime and deposition regime. So we made a lot of simulations for different initial diameter and initial velocity and with a different contact angle to define a regime map. For the heat transfer part, we find out we can get the good we can capture the physics of the drop impact. We can get the drop shape and the hydrodynamic of drop perfectly, but in the heat transfer, we can get the heat transfer accurately for a smooth hydrophobic surface, but for the structured hydrophobic surface, some air entrapped in these micropost structures. So it acts like insulations and reduce the heat flux, so we cannot get this reduction in heat flux accurately. So after that, we just consider the smooth for the heat transfer part. We just consider the smooth hydrophobic surfaces, not structured hydrophobic. From our extensive simulations of the hydrodynamic part, we could derive some correlations for the spreading ratio and contact time. The importance of these two new correlations is that for the contact time, we can relate the contact time to contact angle, and also for the spreading ratio, we could somehow show how the different component energy affect the spreading ratio. In the heat transfer part, we should say we get somehow good agreement, but we should I should emphasize that we should consider the numerical as a complementary for the experiment, because in the experiment, as we capture the pictures from the drop behavior, in the heat transfer we have some problem. We cannot get a good data from the temperature of the droplet. So when we compare the experiment with the numeric, we can see that it is some difference, but where the temperature in the droplet is uniform, we can see that the numerical is exact with the experiment. This difference is due to the difficulty in the experimental part, not deficiency in the numerical part. Also, we made several simulations for the different Weber number, and we could get some data for the cooling effectiveness, and we understand the increasing the Weber number will increase the cooling effectiveness. We made a lot of study. We improved the solver. You can find all the details in these references, but in the summary of what we achieved here, we could implement a method can describe the wetting phenomena, hydrodynamic part well described, can handle real density and viscosity ratio. We find appropriate value for mobility for this kind of simulations, and also our method can predict heat transfer accurately. But for the further simulations, we had two problems. When we have a shortage of high quality experimental data, and also we need to implement heat flux boundary conditions for micro post structure surfaces. If you have any questions, I'm available. Thank you for your attention.